Welcome back, everybody. We are still looking at page 39 of the workbook, and in this video, we're going to talk about a very important definition associated with linear transformations. Okay, let's read through this together. So let V and W be vector spaces, V is our domain, W is our codomain, and let T from V to W be linear. We're going to define two sets. One is called the null space, and the other is called the range of our linear transformation. We have notations for both of those. So n of t represents null space of t, and r of t represents range of t. Okay, here's how these two sets are defined. So the null space of t is the set of all vectors in our domain, so the set of all x and v, such that if we substitute those vectors into the transformation, we get the zero vector out. Okay, so one way to describe the null space is it's the set of all inputs that map to the zero vector. Okay, and I emphasize the word inputs. Okay, and then the range of t is the same range that you know just from ordinary functions. So it's the set of all possible outputs that you could get. So the set of all t of x, where x can be anything in your domain. Okay, so in words, this would be just the set of all outputs of our function. Okay, so the null space has something to do with inputs, and the range has something to do with outputs. All right, and it turns out that these two sets are absolutely fundamental to the study of linear transformations. They're going to come up over and over and over again for the rest of this chapter and then also the rest of the course. So let's take a couple of minutes just to explore these definitions with a couple of examples. Okay, and the first thing we'll do is to reach back to a linear transformation that we came up with back in example 3. It was the one that looked like this. T of AB equals B minus A, 5b minus 5a. Okay, from example 3. We know that that's linear, and let's just play with it a little bit, see if we can find some vectors in the null space and in the range of this linear transformation. Okay, so we might start by noticing that if a and b are equal to each other, like for example, if we calculated t of 1, 1, notice that b minus a is going to be 0, and 5b minus 5a is going to be 0. We're going to get, in other words, 1 minus 1 and 5 minus 5, which gives us 0, 0. Okay, can you think of any other vectors that we could substitute in that would give us 0 out? Well, really, anything where the a and the b are the same. T of 2, 2 would also be 0, 0. T of 3, 3, same thing. And so what that says is that those three vectors that we substituted in, here, here, and here, those are in the null space because we substituted those in and we got the 0 vector out. Okay, so here's our comment on those vectors. 1, 1, 2, 2, and 3, 3 are all in the null space of T. Kind of interesting that they're all scalar multiples of each other. Okay, what about the range? Okay, could we find some vectors in the range? Well, the range is just any output that we can get. So we can find vectors in the range by just plugging some things in. Doesn't matter what. So what would we get if we took t of 1, 0? Well, according to this formula, if a is 1 and b is 0, we're going to get, let's see, negative 1, negative 5. How about t of 2, 0? Negative 2, negative 10. Okay, we could do other things, but the point is, any output that we get is something that's in the range. Okay, so we could look at those two calculations that we just did and make the observation that those two outputs, negative 1, negative 5, and negative 2, negative 10, are in the range. Okay, those are just a few examples. There are obviously a lot of other things that are in the range as well. Okay, let's look at one more example. Okay, for this one, I'm going to go back to the linear transformation that you found in example 4. T of ABC equals 2b minus 2c, 3b minus 3c. Okay, that was the linear transformation from example 4. Okay, and let's just play with that a little bit. Observe that, for example, 1, 0, 0 and 1, 1, 1 are both in the null space of T. Do you believe that? Okay, how would we check that? Well, we'd check it by just noting that if you plug either of those ordered triples into T, you get 0 out. Okay, so T of 1, 0, 0, A is 1 and B and C are both 0, and since B and C are both 0, we're going to get 0 in both of those coordinates. Okay, and you can check and just verify that T of 1, 1, 1, because B and C are equal, those give you the 0 vector as well. Okay, so these two vectors here are in the null space just because when we substitute them into T, we get the 0 vector out. Okay, and we make another kind of interesting observation here. Those two vectors are in the null space, but also any linear combination of those two vectors are in the null space. I'm going to see if I can convince you of that. 1, 0, 0 and 1, 1, 1 is in the null space of T. How would we show that? Well, we'd start by taking T of any linear combination. So a linear combination of 1, 0, 0 and 1, 1, 1 would look like this. And if we use the fact that T is linear, it allows us to pull that apart into A of T1, 0, 0 plus B times T of 1, 1, 1. But we just noticed above that T of 1, 1, 1 equals 0, 0, and T of 1, 0, 0 equals 0, 0. So both of these vectors that I'm underlining are equal to 0, which means that we're just going to get A times 0, 0 plus B times 0, 0, and that gives us the 0 vector. Okay, so we've confirmed then that T of this linear combination really does give us the 0 vector. Okay, so this thing over here then is in the null space. All right, now question for you. Does this behavior remind you of anything that we talked about before? Okay, it might remind you of subspaces. Subspaces have the property that they're closed under scalar multiplication and vector addition. That's the way that this null space appears to be behaving. We took two vectors that were in the null space, we took a linear combination of them, and it was still in the null space. Okay, so what this is illustrating is a very important note here. If we move down here, the null space and the range are actually subspaces. Okay, that's theorem 2.1 in our book, and you might look at the proof of that theorem. I think it's in the book. It might be an exercise. You can check on that. Okay, but the null space and the range are both subspaces, and therefore we could talk about their dimensions. And since they're such important subspaces, we give names to their dimensions. So the rank and the nullity of a linear transformation are given by, the rank is defined just to be the dimension of the range, and the nullity is the dimension of the null space. We're going to do a lot of talking about these definitions, okay, over the remainder of this section.